What was that? Okay. All right, how's that? Better? Hi, so my name is Amit Kapadia. Thanks for having me. It's kind of a nice opportunity to present. I used to work in the academic world and I had more opportunities to present, and since I moved to industry, there's fewer. So it's nice to share some of the work that we do. So I work at Planet Labs, and Planet Labs is based in San Francisco. And we have, I guess, maybe when I started, it was about 3 years ago, or maybe about 100 people working, and we're now at about 450 people. And over that time, we built these satellites, and they're all for Earth observation. So I want to give you a little bit of a history of the company and where we've gone, and also then talk more specifically about the work that I do. And this is building mosaics, and these are at a global scale, and also at a monthly resolution. So this is one example of one of our mosaics. This one was completed about 2 weeks ago, and this is probably our best effort at something that would have the best visual quality. So a lot of the mosaics I'm going to be showing you are really visual products. This is representative of the summer, the Northern Hemisphere southern season, and it's an amalgamation of about 3 years worth of data. So by dipping into 2016, 17, actually 2015, 16, 17, we're able to create a nice homogeneous mosaic. And this is really just like a wide field of view, and we can zoom in and see things at about a 5-meter resolution. So I guess one of our taglines is to image the whole world every day, making the change visible, accessible, and actionable. And I guess when the company started out, that was really the objective, is can we image the entire Earth's landmass on a daily basis? And I think about September of last year, we achieved that. So we currently image about 95%, at minimum about 95% of the landmass on a daily basis. And that's a little bit misleading because quite a lot of the landmass is cloudy, but we actually end up uncovering quite a lot of the world since we do have that daily cadence. This is a first light image. So this agricultural area, I thought it would be nice to put in there. This was released in 2013, and back then we hadn't quite worked out a lot of the kinks. We had issues with the telescope. We had a lot of visual artifacts along the side, a lot of distortions, and since then we've been able to iterate and send up new satellites and improve the imaging as we go forward. So today we've launched about 200 satellites, or I'm sorry, more than 200 satellites. Last year last February, we launched 88 satellites out of India, and that was actually a great event for us. That was what helped us achieve daily cadence. And there's actually a nice video online of the deployment of these satellites. So these were sent into a sun-synchronous orbit, and we were able to get a video feed, and we have all these small little CubeSats being launched into orbit, and it's quite fun to see. With those, we need to be able to transmit that data back down to Earth, so we built a global network of ground stations, and right now we operate 16 ground stations that are capable of about 150 megabits per second. So there's a lot of different areas in which we're trying to advance. Of course, communicating back up and down to space is one of them, and we're trying to improve that transmission. So currently, so this is an image of one of the satellites. These are CubeSats. This is a 3U format. 1U would be a 10 centimeter by 10 centimeter by 10 centimeter cube, and then you just extrude it. So this is considered a 3U. And we try and jam as much technology into there as we can. On the outside, you see solar panels. They're not actually deployed in this photo. This was probably deployed from the ISS, the International Space Station, and one of the astronomers was able to take a photo of it. You can see the telescope in there, and then you can see the antenna sticking out as well. So currently we're imaging about 1.2 million images per day. I looked at a graph, and that's actually maybe on a low end. So we do kind of oscillate a little bit on what our acquisitions are. So at minimum, we're at about 1.2 million images per day. That equates to about 100 million square kilometers per day. And again, that's over the Earth's landmass. In order to maintain this data stream, we're operating about 40,000 virtual machines during peak usage. So again, that's something that we fluctuate. We scale up and we scale down according to the workload that we have. I've never seen it go past 40, and it was quite an achievement when we hit 40. Over the past few years, it was always an achievement when we hit a certain level of VMs. I remember when we were operating 10,000, and then 12, and then 18, and those were all stunning numbers. And we made some changes to the infrastructure, and now we can get up to 40,000. I wanted to share a few videos. Let's see, so over the time that I've been at Planet, we're kind of bombarded with a lot of very interesting visuals. We're imaging the Earth. We see a lot of events that happen on Earth. We see geopolitical events. We see natural disasters. So there's a lot of stunning imagery. This, though, is probably one of the coolest things I've seen while I've been at the company. And what I'm going to show you is this is a launch that happened in July of last year. It was out of Kazakhstan, and I think we had about 42 satellites during that launch. So at the time, we had more than 100 satellites in orbit. And just a few days before launch, some of the folks who work in the satellite controls realized that we might actually have a nearby pass over the launch site that corresponded with launch time. So when we realized that that was a possibility, a few folks kind of went to work and figured out how we can actually do a maneuver and focus one of the satellites onto the launch. So it was actually kind of getting lucky at the right place at the right time. And then also doing the maneuvers are quite complex because these satellites, they don't have propulsion on them. So we're constrained with magnetometer to help us point down towards Earth and a few gyros. So it's all mechanical motions. So I'll show you this. The images are a bit oblique, but I'll play it a few times, and what you're about to see is just one of the launches that sent up 40 of our satellites, imaged by another one of our satellites. Play it one more time. Yeah, so I found that fascinating mostly in the complexity of the satellite maneuvering that had to be involved. Another interesting thing is that so the earlier iterations of the satellite were launched into an International Space Station orbit. That's about a 400 kilometers above Earth. And those satellites typically had a lifespan of about 1.5 to 2 years. So of course we've lost quite a lot of them, and they would burn up on re-entry. These things are small. The debris never actually hits Earth. But just by chance, an amateur astronomer happened to be tracking some satellite debris, and they captured one of our re-entries. At the time, folks didn't quite know what this was. I thought maybe it was meteor, maybe it was satellite debris. And then again, folks who are on our satellite controls team figured out that it was a re-entry of one of our satellites. So I think this might be one of the first videos of that. So that's another interesting thing to come across. Is it? Yeah, let's see. We'll play once more. Yeah, so it's coming from the right side of the frame. It's coming through the center right now. So there's a lot of eye candy. So I want to talk a little bit about our compute, and then a little bit about the mosaicing process, and then I'll show you some more visuals. So currently, right now, we're processing about 5 terabytes per day. So these are scenes that these are images that get acquired from satellites, they get downlinked to Earth, and then they get put up into a cloud-based platform. We're running on Google's cloud platform. If I was giving this presentation about a year ago, we were running on Amazon's platform. So there's a team that was dedicated to that transition. I think that must have been a pretty formidable effort. So we run between 25,000 and 40,000 VMs, depending on our workload. Sometimes we have backlogs that we need to fill, and we really need to crank it up. Sometimes my team, the Mosaics team, needs extra compute, so we have to crank that up as well. So this is really a shared resource among all the developers at Planet. We have teams that are responsible for building mosaics, like myself, ortho-rectifying the images, that's taking these images and ground locking them to the Earth. That's a very computationally intensive task. Preliminary processing, calibration and validation of the imagery. So there's a slew of different tasks. And what made sense to us early on was to create this very homogeneous compute environment. So the majority of these instances that we operate They're single core and they have very limited RAM, so they have about 3.75 gigabytes of RAM. And the idea is to just write very simple programs. So there's probably none of us at the company that are really in the depths of writing multi-threaded, multi-core software. There's folks who do experiment with that, but for the most part, everything that runs in production is pretty simple, very just single-threaded programs. And the strategy that we take is we just parallelize across volumes. So if we have a batch of 10,000 images coming in, each one of those images gets its entire worker. And the languages are mostly in Python. We do write a little bit of C++, and every once in a while we dip down to Python. As far as Python libraries, GDAL and OGR, those are geospatial libraries that live in the open source. They are useful for doing image manipulation or working with vector data sets. And you can imagine doing transformations from pixel space into world coordinates. So those are tools that you would want to use if you're really interested in the geolocation of your image. Rasteria, Fiona, Shapely, those are more like handcrafted Python bindings around GDAL and OGR. So it makes it pretty easy to get NumPy arrays out of your raster data, NumPy arrays that we also kind of maintain the world coordinate systems to as well. NumPy and SciPy, scikit-image, scikit-learn, Cython, TensorFlow was added recently. We have a couple experiments that are using that. Those are going to come into production too. And then Dask. And Dask is quite interesting because, like I said, we run on these single core machines, and I don't believe we run any large production tasks with Dask, but we've done a lot of experiments with it. So if we have an R&D project and I'm running my own instance, which might be a different flavor than what we run in production, I might have a lot more RAM at my disposal and a lot more CPU power at my disposal. On the other hand, to run Dask within production is quite interesting because we can run out-of-memory operations even if it is on a single core. So a little bit about the mosaicing workflow. So we take the entire world and we grid it up into tiles. And then for each tile, we query against a Postgres database or PostGIS database, which is geospatially aware. And we look for intersecting scenes. We rank them according to some metadata. We normalize the images using some auxiliary data sets. We assemble the tile until filled, and then we post-process it to remove these image-to-image boundaries. So I'll step through a couple visuals that explain each one of these steps. So this is an area, this is the Bay Area, and this is just an example of how we might grid it up. Let's say we're working with that highlighted area. One of our workers, that's one unit of work. And when we grid up the tiling scheme that we use, when we grid up the entire world, it ends up being about 3.7 million tiles. So we'll queue those up, and each worker becomes responsible for computing one of those. So we rank scenes, and I guess like our intuition led us to believe that what we were really looking for are any scenes that have few clouds in them. We don't want to create mosaics that are filled with clouds. We want to actually see the ground, and then sharpness. Let's see, the sharpness metric is actually computed using a Gaussian gradient method from SciPy. So it's actually quite nice and simple to use, and it's a good proxy for sharpness. And that's important mostly because there's areas really in like the industrialized world or any areas that might have a thick atmosphere where you might have a thick layer of pollution over them. And by looking for the sharpness of an image, what we're really looking at is like the relative sharpness of these images that intersect the same area. It turns out to be a decent proxy for whatever atmospheric effects might be between your satellite and the ground, or whatever pollution might be between the satellite and the ground. So we can actually rank according to that and use sharpness as a proxy for that. So these are all made available to us upstream of the mosaicing pipeline. So at this point, we haven't really touched any pixels. We're just looking at metadata. We don't have to transfer any imagery back down to our workers quite yet. The next thing that we want to do is we want to normalize all the images that go into a single tile. And since we're building monthly mosaics, what we've decided to do is build monthly mosaics using a lower resolution data set. So we use MODIS, which is which are 2 satellites that are operated by NASA, and we build out these 500-meter resolution monthly mosaics for MODIS. So we've got a representation of what the world should look like every month. So this is the auxiliary data set that I mentioned before. So if we have a bunch of scenes and we want to actually compile one of these tiles from them, here's an example where we have 8 input scenes. And keep in mind, like we're building these global, these monthly mosaics. So these scenes could have been taken at any point during that month time span. So they could be taken by different satellites. They could be taken during different atmospheric conditions. There could have been some ground change during different acquisitions. So it's important that we normalize these images. And since we're after a visual product, we can actually throw any kind of hammer routine at it. We don't have to worry too much about building out a physically correct product. So we take those color targets that I just showed, and we compute a regression. We look for the same intersecting pixels, and then we fit a regression to those. And what that does is it kind of gets us all in line. So all these scenes end up being normalized, or at least relatively normalized to one another. And at this point, we've transferred these images to the worker. We know that they're going to contribute to the final tile. We're not transferring any images to our workers that we know are not going to be contributed to the tile. So once that normalization process is done, we assemble the tile. And here you should be able to see these image boundaries. So we've got this like 2-step process. One of them is this regression method that I mentioned, where we use this auxiliary data product, and we look for a good mapping to map those colors from one image onto the other. But it doesn't quite get us into like a seamless composite. So we have one more correction that we do, and this is like a post-processing operation that we do on this tile afterwards. And this is where we jump into the gradient domain. So let's see, on the right, this is more or less, like passing it through an edge detector, running a convolution over the image. Here we actually use a Laplace kernel. And the strategy here is to take this image, and everywhere where we see these hard boundaries, we actually know, we keep a labeled image so that we know exactly where these scene boundaries are. And instead of running a normal convolution, this was an opportunity where we got to write our own convolution operator in Python. We wrote a convolution operator that allows us to convolve every single pixel. However, when it butts up against another image, we never sample a pixel from a neighboring image. Instead, we make an approximation. And what that allows us to do is produce a gradient that looks like this. So it's much smoother, and there's been approximations made to those image boundaries. So I'll flip back between those two. So there's the ones with the scene boundaries. There's ones with scene boundaries that have been approximated. So this gradient actually looks somewhat smooth. And then going from the gradient back to a smoothed image, this is actually quite an interesting topic. I'm not going to go into too much depth about it, but it opens the door to actually solving like a boundary value problem. So there's some interesting algorithms that we throw at it. There's different cases in which we solve from this image to this image, but it's given us the opportunity to write some solvers, taking an iterative approach and also a spectral approach, depending on how complete our tile might be. So when we do this, and we do it for the entire world, and we've thrown a lot of this compute at it, we produce a nice global mosaic, and we've made a best effort to remove any of these image boundaries as possible. So the next one that I'm going to show you, so we've been doing this since January 2016, so we've got about, 24, 28 mosaics. So this is an animation of all those mosaics over time. So there's areas up in the northern latitudes, like right here, where you see there's data missing. That was back in 2016 when we were limited to satellites in the International Space Station orbit. They were constrained in the latitude. And once we got satellites into a sun-synchronous orbit, that allowed us to collect more data at higher latitudes. So you can see the seasonal effects. You can also probably see some flaws in here. You can definitely see some flaws if you zoom in. We always have issues when the winter months come around because it's quite hard to build mosaic during winter months. Snow is very sporadic. It might snow in one area, the color target that we use might not represent the snow on the ground. So those are some things that we're trying to figure out. Yeah, other things, it's a little bit sparse in those earlier years, but these days we actually build these fairly nice complete mosaics. Let's see, so what's next here? Other mosaics that we do, so we do have this pipeline, and it's not just for building visual products. We have a team that's dedicated to calibration and validation. So this is a false color representation of this area. So Napa is actually, anyways, Napa is this town right here, and these, what this shows are both like a pre-disaster and a post-disaster mosaic of when the wildfires were happening last fall. So right here you see a lot of these burn scars, and then right here you see a pre-fire mosaic. So one of the things that these data allow us to do is see both like pre-disaster and post-disaster changes on the ground. This one's interesting. I think we released this image comparison yesterday. So in Hawaii we have this volcano, Kilauea, that's erupting right now, and it's been kind of warning us for the past couple weeks. So here we have an image that was taken in January, followed by an image that was taken in May. And what you see in the lower right is a lot of lava flow. So these are things that we're capturing every day. So whenever there's an event on Earth, we usually can see it unless there's some clouds that intrude on us. Here's a little bit more eye candy. So this is a solar farm that's being built in China right now. This is really just to kind of show our temporal cadence. So you can actually see the progression of that construction. There's not a lot of effort made to normalizing each frame against one another, but we can still see a lot of the construction in progress. Here's another one of sandbar forming, I think off the coast of South Carolina. Again, it shows our temporal cadence. So you can see this island actually forming slowly over time. So it's becoming a fairly deep data set, and we can start making these animations. And you know, our next step forward is to actually automate the detection of a lot of these changes on the ground. We have a couple of resources for anyone who's interested. We do have a developers program. If you sign up at planet.com, you can sign up for an account, and we'll offer you an API key. We do have a couple open data programs. We offer data of California under a Creative Commons license. The only thing that we do is that we delay the release of the Creative Commons license by 2 weeks. So if you want, you can get 2 weeks. You can get images of California 2 weeks ago under a fairly liberal license. We also have a disaster data program. So whenever a disaster has been declared, we'll go off and look into our archive and see what's available and make that available to people who would find that relevant. And then we've also been working with researchers who use our data. And we do have a couple publications up there. I think probably the most interesting one that I've found is that there's a researcher who's looking at our imagery to find precursors to avalanches. So there's a few things up there if you'd like to read. I think that's it. So I'm happy to take any questions if you have any. So, thanks.
Thank you for that really interesting talk. So my question is about different types of imaging. Is everything in the visual range, or can you also do like infrared or like different energies of light and kind of capture different information about how the planet is changing, like capture temperature information and stuff like that?
Yeah, so we are limited. So let's see, early on we were only producing in the visual, just RGB, and then we started adding near infrared because there's a commercial interest, at least for agriculture. So all of our most recent satellites also have an infrared component, and the mosaics of Napa actually show part of the infrared component there. So we do have near IR. And then we also operate some satellites that come from this company called Blackbridge, which was acquired maybe about 2 years ago. And they also have, let's see, red, green, blue, near infrared, and I think they call it red edge, and I think it's not quite mid-infrared, but it's kind of butting up against mid-infrared wavelengths.
Okay, yeah. Interesting. Thanks.
Great talk, Amit. My question is about the processing. I have the impression that a lot of the products still require a human at the end of the pipeline. Is there plans to automate that, or this is how it should work? You know, a human needs to be held accountable for the decisions or whatever is the event that is happening in this kind of imagery.
Yeah, so I think that depends on the kind of processing that we're talking about. All the incoming data gets picked up automatically and gets processed and pushed through our pipeline automatically. The mosaics that we produce on a monthly basis require one of us on the team to push the button and say go. And for the most part, it's automated, and we have to deal with failures as they come up. As far as like releasing data to the public, that is a very manual process. Someone has to approve it. And we do look at external organizations that declare states of emergency and respect the decisions that they make and follow that accordingly. But it is still a manual process. I can't really speak to any efforts that we have to automate that completely. But all the images that you could access through the platform, for the most part, that is an automated process. But that is behind like a paywall. So, yeah.
To which extent it's desirable?
I'm sorry?
To which extent it's desirable actually to automate? I mean, automation can be a good thing and a bad thing.
Yeah, yeah. So the majority is automated. So from satellites to downlinking to initial processing to what actually gets disseminated to external users. I would say the majority of that is automated. Special cases like when we provide data for disaster response, that there's a human involved there.
So within your analysis pipeline, are you, it seems like you'd be transforming coordinate systems fairly often.
Mm-hmm.
How, like, is that handled by the Python libraries that you're using, or is it, like, how do you track that?
Yeah, so some of the problems, yeah, they involved a lot of coordinate transformations. A lot of the geospatial libraries have this built in. So GDAL is a perfect example of that. It knows how to do a lot of image operations. If you want to scale an image up, scale it down, but it knows how to do that and maintain the coordinates that you have available. So if you do open an image using one of their bindings, there's always this coordinate system information alongside that you have at your disposal to make those transformations. Those are fairly well written functions in these libraries. Yeah.
So I'm interested in real-time analysis. I'm wondering if you took one of your Google Cloud instances and launched it with your camera, would it change the way you operate dramatically? Could you imagine things that would happen in real time that would change the way you designed the search or the survey?
Yeah, that's a good question. So we have, at this point, we have fairly limited compute power on the satellites. Is that what you're referring to? Yeah, we have fairly limited compute power on the satellites. There's also some interesting stories there. I think that the only thing that we're really trying to push towards is how do you just discard data that might not be useful? So clouds would be an interesting one. I think there are people who are actually interested in that imagery, but they're few and far between. So there have been efforts to put, for instance, like a cloudy image classifier on board so that we don't have to transmit them down to Earth. There's some interesting, so we're regulated partly by the NOAA, and there's some interesting regulations which I think are going to be slowly outdated, but as soon as we transmit an image down to Earth, as soon as it leaves a satellite, we're not allowed to discard it. So even if we have this vast catalog of cloudy images, we are not legally allowed to discard it. I think they're starting to make some exceptions, but it makes the case of doing some onboard processing more attractive. Yeah.
So we have time for one more question. Just a quick question about the kind of cameras you have on these satellites. I know from experience working with primarily smartphone cameras, the image you get is never veridical. There's always some sort of processing under the hood to sharpen up the edges and whatnot. Mm-hmm. Is it the case that your sensors just deliver totally raw, unprocessed images?
That's a good question. I might not be the best person to explain that. We do a lot of processing. Yeah, they can be kind of brittle. I don't know how to best explain that, but yeah, we do get a fairly raw image, and we do have to process quite a bit of it. We have our own custom drivers to remove certain anomalies in images, and that's a lot of the preliminary processing that every image goes through.